There was. Hello, everybody. My name is Phil Simonowski, and this is 272 Summer CAD Class. This is Class 7 of the series. And a little bit about me, if you'd like to read more about it or learn about it in previous videos. And today we're going to, similar to last class, we're going to continue our work on gearbox design, as well as learn some more about different COTS components that we can implement. We're going to get more familiar with different features and also get more familiar with inserting parts into an assembly from the standard parts library, from other libraries like MKCAD specifically, and then parts that we've individually created. And then we're going to continue to move and mate parts around to build assemblies up. So moving on, last class we left off with this little very simple 2-motor, 1-stage gearbox design. And maybe this is something that could be used on a drivetrain. Now, this is only currently driving one wheel, but there's potential that if we do some modifications to this design, we could have it drive multiple wheels, like if we have a tank drive robot. So does anybody have any questions starting out? All right. For those of you who were here last class, how far were you able to get? It's okay if you didn't get very far at all.
I was able to complete like half-ish of my gearbox.
Okay. Would you want to share what you have so far?
Sure.
London, you too, get ready. I'd like to see what you have made up to this point. Oh, sweet.
So I'm kind of having problems where here where the gear is overlapping with this rod.
Mm-hmm.
And
very good.
And also nothing turns. I think it's because I'm only using fasten.
That's exactly why nothing's turning. So you can actually edit any one of the mates, like that you've made before, and make them, instead of fastened, use revolutes.
So if I want for example, this gear to rotate, would I?
Yep. Change the mate that attaches that gear. I think that's the motor, actually. You don't want to do that one.
Oh, yeah.
What you can do, Vihan, is right-click on the gear.
Here.
Yep. And then hit Show Mates. It's like just under halfway down. See Show Mates? Oh, you passed it. There it is. And that will show you all the relevant mates. And you can see in the tree on the left. Yep. So that's the one that you want to do.
Yep.
So if you edit that one, you can change it from a fasten to, if you click the drop down, become a revolute.
Cool.
And now it should rotate. So if you click checkbox, now you should be able. Oh, wait. Click undo for a second. You haven't fixed any of the components in your assembly, so they're still moving. So what I want you to do is click on the plate, like the blue plate that we made.
Yep.
Right click on it and click Fix. And now you should be able to rotate that gear without everything moving.
Yep.
There you go.
Yeah. And I'll do that the same with these guys.
Yep. Well, here's something to consider, right? You want the shaft and the center gear to rotate together, right?
The shaft, this one, yeah.
Yep. So the shaft and the gear are going to have a fastened mate between them, but the shaft itself is going to have a revolute mate to the plate.
Isn't there the bearing here?
Yeah, so you want a revolute mate.
Okay, so
You can also do, okay, that's true. You can do a fasten mate to the bearing and then do a revolute mate on the bearing to the plate. There's
okay.
a number of ways you could do it. Sometimes it's not even important that these things rotate. Like sometimes it is okay to just totally make fasten mates for everything.
Yep.
But you do bring up a good point about the shaft spacing here, and so you have a big problem that you want to resolve. And this is kind of the beauty of CAD, is that you can visualize that this is going to be an issue before even building anything, right?
Mhm.
Like that's huge, absolutely huge. So remember, I think that you're trying to build a two-stage gearbox, if I'm correct. Is that right?
Yeah. So like on top of this gear, there would be a 10 tooth gear, and then on here there would be a 20 tooth, I believe.
Cool. So two things. I don't believe that they make a 10-tooth gear that fits on a half-inch shaft, on a half-inch hex shaft.
Yeah, I was seeing that.
Yeah, it's just too small. It'll be too little material. So what you're going to need to do is make that gear a different size.
Yep.
And you might still have to make the other gear a different size as well.
What
Like
gear
the
would
big gear. Well, I would recommend, I think 12 tooth comes in half-inch hex, maybe.
Okay.
Possibly. I'm not entirely sure.
So would I still use a 20 tooth gear?
You may need to use a larger gear. Why don't you change the center spacing on that second gear train so that it ends up with a 12 tooth to a 22 tooth and see if that's far enough apart.
Cool.
And remember, you used an equals constraint on that first center to center sketch, right? C to C.
Yeah.
So you're going to have to delete the equals constraint between the two small gears, right?
Yeah.
Yeah, not that one, that one. Yep. So you're going to need to delete the equals constraint, not, yep, on that one.
So
Yes.
I would click here.
Yep. Click that and then click delete. And then you're going to change that. So do another dimension, which is the D key for a shortcut.
Yep.
And do you remember the equation?
It's the gears on the divided
teeth.
by the teeth, yeah.
Yes.
The teeth divided by the DP.
Yes, good. The diametrical pitch is the word. It's kind of a weird word, but so try 12 and see what happens. And your model will automatically update once you do this. So now click OK, click the green checkbox up there, and your whole plate will adjust in size automatically. It'll take a second, but oh yeah, when you go back in time, you don't need to suppress.
Okay.
You can just edit a sketch in the history, and then when you click OK, it'll just build the rest of the stuff.
Cool.
It'll redo it. So now go back to your model and see if your shaft is still running into the other shaft.
Just a tad.
Yep. So that's still going to be a problem. So that tells me that you either need another bigger gear on the small one, or if you still need that reduction, then you need a bigger gear.
I guess I'll use a small, bigger gear then.
I would make the bigger gear bigger if I were you, if only because that will keep your reduction very high.
So I'll take this one and make it big.
No, not that one. The
12
gear,
one?
the gear, no, the gear that you don't have on the other shaft yet.
Oh, this one I'm going to put.
Yes, that one. Yep. So figure out what size gear you can use there and which ones exist. You're also going to have to delete that equals constraint as well.
Yeah.
So if you edit your C to C sketch, also click the P key like P for fill. There you
Oh.
go. You hide all the planes, and it makes it a little bit more easy to work with. So that, not that one. I mean, you can delete that one, but not that one.
Okay.
The
This
bigger
one.
one. Yes. You can delete that.
Yeah.
And then put a dimension on that of, so it looks like it was 2 inches. And how many teeth would that be?
10.
No.
Oh, sorry. 40.
Yes, good. Good. Did everybody see how Fihan did that? He took the total number of teeth and divided it by 20 and figured out that he needed 40 to get 2 inches. Well, let's go for a bigger one. So let's go for like a 40, I think a 48 tooth gear is a pretty common one.
Okay.
48 divided by 20. And now click the green checkbox and it rebuilds your whole plate for you. And now go back to your assembly and see if it's still a problem. That looks good.
That works.
That looks really good. Now, here's another thing that you may want to try that might make your design a little bit more interesting. If you wanted to, these gears don't have to be in a line with each other. And
Yeah,
usually in gearboxes, they're not. They're usually really tight together, like in triangles, to try to minimize the overall size of the gearbox. I would say for now, keep it in line, but at a later point in time, I'd like you to delete that horizontal constraint, and then you can take the things and move them around and see how your design changes.
Yeah.
Okay.
Yep.
So I think you're on a good front. Find a 48 tooth gear to put on there and find a 12 tooth gear with a 1/2 inch hex ID to put on the hex and continue your design. I will tell you now that those hex shafts that you have, those aren't really the ones you want.
Which one would I use?
Click the MK CAD and look up. What happened to it? There we go. Go to, scroll down. There should be a tab called shafts somewhere. There you go. Go to shafts. That one's fine. Configurable is good. And you just want a Vex hex Thunder hex. Do you see that one?
Yeah.
Yep. So click that. And then 36 inches is way too long. Make it more like, I don't know, 4 for now, probably, or 3. And you can change this later, so don't worry about it. And don't make it Thunder hex. Take off. Okay, you can leave it, but yeah, take off the Thunder hex. Just make it hex for now. We'll learn about Thunder hex later and where it's useful, but for now, we're just going to use regular hex.
Cool. Where'd it go?
There it is. Yep, that's the new one. Now, do you remember that replace function that I used last time?
Not exactly.
Okay, if you wanted to replace those shafts you already have in there now and still like retain all those other mates,
Yep.
They'd still be broken. You'd still have to fix them, but they would at least exist, right?
Mm-hmm.
You could right-click on one of those shafts and do replace.
Yep. This.
Yep. And click the checkbox that says replace all instances because you don't want to just replace one. You want to replace all the ones. Mm-hmm. And then where the red box is, do you see the red box up in that same window?
Here.
Yeah. Click that. And this brings up this window you should try to get familiar with. This is the part navigation window or assembly navigation window. This is how you insert things into an assembly normally if you're not using MKCAD. Okay?
Yep.
So you would go to Other Documents. You see Other Documents tab at the top?
Yep.
And just type in the search, or actually, sorry, click Public first. You gotta click the Public button. And then search MKCAD, all one word. M as in Mississippi, K as in Kansas, and then CAD. Yeah, there you go. And scroll down until you see shafts and where it doesn't say copy next to it. You don't want to use the ones that say copy.
Why?
Because the copy ones are ones that people have made a copy of. And we want to use the real MKCAD ones, not ones that people have made a copy of.
Okay.
There's people that don't know how to use this MKCAD, and they think that they need to make a copy of the library and put it in their own Onshape to get it to work.
Okay.
And that's what you do in other CAD programs, but in Onshape you don't need to make a copy of it. Maybe try this. Type in MKCAD space dash space and then type shafts or just shaft. Yep. Search that. MKCAD shafts configurable. I think the first one, like this, or the second one down. That one, yeah. Yep. And what you're doing is you're finding a part to replace those other parts with. Okay. And you see this has that same hex thunder hex, right?
Yep.
That's the same one that we chose before. So click that drop down and do the same thing you did. Uncheck the thunder hex and do 3 inches or however long you want it.
3 inches.
And then click generate. And that might take a minute to generate. Should work. Anyway, just click on the hex thunder hex at the top. Right to the left, up, like right above that. Click that. Yeah, that should work. Oh no. Click it open again.
Should I say generated down?
Yeah, I don't know what's going on. There we go. So you see that thing that just showed up there?
Yep.
Yeah, so click that. And that replaced all of your shafts with that new shaft at once, so that you didn't have to do it individually. Now it broke your mates because it doesn't know which face is which face between the two.
Mm-hmm.
All right.
So I'll check mark this.
Yep. And then you're going to need to edit your mates and fix them back up again to get them in the right place. And the ones that are broken are the ones that are attached to the shafts. That's going to give you a hint.
So this one, we would
right click, edit. Yep.
Okay.
And then click the X next to the red line in the blue box. You see the blue box up there? Yeah. So you want to delete out the previous location of where that mate was mated. And then you're going to click on the new location, which is going to be on that face. On the end of the hex.
It's hard to see.
Yeah. Do you have a mouse with a scrolling wheel?
Yeah, I'm using it.
Yeah, zoom in further. You can zoom in indefinitely. Keep zooming, keep zooming, keep zooming. There you go. Now you'll be able to select it easily.
Like this one or something?
No, on the shaft.
Oh,
not in the bearing, on the shaft, yeah. And not the corner, the face of it, the end of it.
Yes.
Yeah. Yep, that right there. There you go. Oh, it looks like you made it the face of the bearing. Delete the bearing mate.
Oh, okay, yeah.
Delete the one on the bearing where it says 1/2 inch in the blue box up there.
So this one?
The bottom one. No, the bottom one, I think.
Yeah.
Yes.
Or is it?
Oh no. Yeah, sorry, it was the wrong one.
Oh.
Delete both of them just for a second. And you can do this to any mates. You can add and remove them. All I want you to do for the first one is click on one of the round edges of the bearing. You don't need the face. You don't need the hex face. Just one of the there you go. Perfect. Yep, that's it.
Yep.
And then you want to click on the shaft on that face.
This one?
Yeah. Take off your offset. So uncheck the offset button.
Yeah.
Or put 0 in there. There we go.
Then should we like move it down a little?
You can. What I would suggest to do that is change where it's mated to the other side.
Okay.
So delete the mate that you made on the bearing.
Okay. So
No, not over there. In the blue box. In the blue box.
Okay. So that would be this one.
Yep. And then put it on the bottom side of the bearing instead.
Yep.
On the outer edge. Yep. There you go.
Yep.
Perfect.
Okay.
Now click the checkbox. So you can edit mates. This is actually a really good exercise in showing you how this all works, showing everybody how this all works. Even when you have broken mates, which is when you see the mates go red and they're not very happy, you can fairly easily diagnose where the problem's coming from, and you can edit those mates so that they become happy, or you could just totally delete the mate entirely and start over again. So Vihan, I'm going to let you keep going here and editing, fixing up your mates, and maybe putting a plate on top as well as the one that you have that's mounted to the motors.
Yeah.
And we're going to move on to...
What type of
Sorry?
what type of shaft should I put like right here?
Right. Where?
Like here. Like to hold up.
I would say make a custom spacer kind of like I did. You remember that?
Yeah. Spacer.
So it's just a circle and a circle. Or yeah, you could do it in there. There should be, if you look in spacers, there might be one that's called spacers. Yep, there it is. Spacers. See it?
Yep. So I would use the
just do nylon spacers, and that's a configurable part.
Yep.
And then you can change the OD, the ID, and the length.
Okay. Cool.
All right. There you go. All right. Awesome. Who would like to share next? London, would you like to share what you have so far? And it's okay if you haven't made any progress since last time.
Yes, when this tab loads, I swear I logged in on Onshape, but now I'm literally just waiting for the tab to load because the internet's still going in and out here.
Okay, well, no worries if you can't, but just keep trying, all right?
Yeah. I just wanted to talk to my mom to see if she could restart the internet because it may be because everyone's using it at the moment. So
got it. Everybody's on TikTok and Facebook and YouTube and
yeah,
whatever other website anybody uses. No worries. Take your time. Isabella, welcome. Thanks for joining us.
Yeah, sorry I'm late.
You're fine. You're a busy girl. Were you? I don't think you were with us last meeting, were you? I forget.
On Monday?
Yeah.
No, I didn't realize there was a meeting on Monday.
All good, no sweat. I didn't realize that the meeting invites weren't going to get sent out. So what we were doing is, you saw my screen before, right?
Yeah.
I would like you to build a gearbox. That's what we're trying to work on.
I had started on meeting 5, so I've got some things.
Okay, cool. So would you like to share what you have so far?
Sure. Did you...
Perfect. All right. So it looks like you did mate the bearing to the plate. That's good. And you mated the shaft to the gear. And it looks like you were working on mating the motor to the plate, maybe?
Yeah.
Perfect. Oh, good work. So keep on working on that. Can you zoom into your pinion gear, which is the small one?
Sure.
All right, cool. So that is the right gear that has, do you see how it has a keyway on it?
Yeah.
They make another one of those that has like a spline shaft.
Yeah, I went for the sim one because I didn't see one specifically for the Neo.
The Neo shaft is the same as the sim shaft.
Okay.
And that's okay if you don't know that, but just the Neo shafts are made so that they work with all the sim components. The sim were an older style motor that weren't quite as powerful or as fast. The Neos are smaller and more powerful, so everybody's moving to them now.
Okay, that sounds good.
So keep mating, and you should be good. How are you setting up those your far side plate? Do you have any idea how you're going to do that yet?
No, not yet.
Okay, I'm gonna give you a tip or a helpful hint here. Open MKCAD. I don't know if you saw where Vihan got that spacer from.
Yeah.
You could just type in spacer. There's a whole drop down that is spacers, and don't go to that one. Go to the configurable one, and then you'll be able to adjust it as you need. So yep, nylon right there. And then you could just insert that, and then you can always change the values later. There you go. You have a spacer. Now you can put that in place, and you can change the length, change the height.
Okay.
One thing I would suggest, though, none of your parts are fixed. You should always have one fixed part or one mated part to the origin in every single assembly.
Okay. Also, like, if we wanted to get bolts in here, how
Yep.
would we do that?
Sure. So you would click on. You can do it a number of ways. I like to click on the hole where I want the bolts to be. So just as an example, and then you can click Insert. And it's going to insert from the standard content library. Yep. And then you can select what kind of bolts and what kind of things.
Okay.
So you probably want bolts and screws, and you want socket head is probably what you're looking for. Yep.
Thank you.
You could do a button, or you could do a regular socket head cap screw, or you could do a flathead screw if you wanted to.
Okay.
And another tip, you should look on the manufacturing information page of the Neos, which is on Rev's website, for what kind of thread goes into those motors. And then you should be able to pick the right bolt from that. Okay?
Okay. Thank you.
Cool. Awesome.
I'll stop sharing.
Steve, do you have a gearbox to show that you'd like to share?
Sure.
Perfect. Let's see what you
Mace,
got.
how do I share? This will share.
In Google, there is a right by the leave call button and the hand raise button. There's an arrow. There you go. You figured it out. Beautiful. Beautiful.
So I'm not very good at mating, and then I start using offsets to try to make it go where I want instead of getting the correct mate.
Yeah, generally, offsets are useful, and you will use offsets from time to time. But for kind of the simple stuff that we're doing here, we should generally try to stay away from them. So, can you show me what in which place you have an offset?
Well, so here's one I can't get the motors that flush to the plate.
Okay, so I'm going to show you how to fix that. You selected the upper edge of the motor hub there. I want you to, do you see the blue box over on the left?
Mm-hmm.
Click the X next to the Neo brushless motor. And now go back into your window and select that bottom corner of the Neo motor instead of the upper edge. And here's another trick. You can isolate the motor. If you right click on the motor, you can hit isolate. Sometimes it doesn't work. It's really annoying. This is annoying to me. It doesn't deselect the other thing you're mated to. Right? Like it should not show the plate, but it's showing the plate still.
Can I hide it?
You should be able to, yeah. Hide it over in the left pane, like over on the far left. Yep, right there to the right. You see the eyeball? There you go. There you go. Now you can click that edge that you want to click.
I want this edge.
Yep. Click OK and see, click OK and see what happens. Because you got to exit the isolate, yeah. All right, undo that. I don't know what happened. So, yeah. Which mate is that? Yeah, so delete the one on the Neo brushless. So that's in the right place.
Like this. And I want this, right?
Yeah, I think so. There you go. And now if you show the plate again, there it is.
Oh, beautiful.
Yep.
Okay.
So again, there are instances you will need offsets for certain things, but none of the stuff that we've done so far really necessitates offsets. The only place where I did do an offset is on the spur gear, on the gear
Oh, I
attached
did
to
do one on that, but that one kind of made sense to me.
Yep. So normally you don't want to have those gears all the way up against the bearing for obvious reasons. The gear will grind actually against that bearing. So yeah, that's one of the places where you don't want that.
And then my hex shaft is not aligned, so I don't know. I made it that wrong too.
You can edit that if you right click on the gear or on that mate there. But if you click on there on the gear, you can hit show mates and it'll show all the mates that are on that gear. And now if you see in the left window pane, it showed that fasten 3. Right? And if you edit that one.
Which this one?
Yep. See how it's unhidden?
Okay.
And then do you see there's a little rotate button at the bottom? It's right next to the flip direction button. Click that once. Yep. Now it should be rotated correctly. There you go.
Yeah. Okay. I think I'm in the bearing wrong too. Is the problem?
You're mated to the bearing incorrectly?
Yeah, I think that's the same issue.
Okay, then you should be able to fix that one as well if you show mates on the bearing.
Let's go. Yeah. See?
Yeah, so right click on the bearing and hit show mates, or if you know which mate it is, then you can do it that way too.
This one.
So edit that. But you can right click edit or you can just double click. And then yep, there you go. That's it.
Oh, beautiful.
There you go. And in a lot of our designs, it's
That re-screws up the other gear.
oh, you know why? Because your gear's not mated
Fast.
to the shaft.
It's not what?
I don't think it's mated to the shaft. I think it's mated to the bearing. I think that's what's going on.
Let's see.
Which you can do it either way. You can mate it. It really doesn't matter. There's not a right or wrong way, but generally you want to do it in the order of operations that things are moving together. So like the bearing is attached to the shaft. So you generally want to rotate the bearing and the shaft together. And then the shaft is attached to the gear. So you generally want to mate the gear and the shaft together in that order.
Okay.
Cool.
Did I pick the wrong spur gear?
So these spur gears, some of the new spur gears that they have a lesser tooth count, but they use a larger center to center distance. And they do this by kind of like messing with the geometry of the tooth. So you can use that one, but you have to change your center to center tooth distance. And you might have to look up the manufacturer's information on that. So I believe that that's a Rev gear, or it might be a Vex gear. That number is a Vex part number. When you see a 217 in front of it, that is a Vex part number. So if you look up that part number on Vex's website, you'll be able to see what the center to center distance is supposed to be of that gear. It's kind of a little exception to the rule of the number of teeth divided by 20. When they make these really small gears with like custom geometry, what they're doing is they're making your possible reductions from a gear train higher with a single gear and a single pinion. But they have very custom kind of unique geometry that's being used for that. I'm almost sorry that I like exposed everybody to that because it's very confusing. What you can do if you want is you can switch to a 12-tooth gear and change your layout sketch to a 12-tooth gear. And then it'll work correctly.
Whoa. Okay. Oh, it's now.
Did you use the right center to center? I think you did.
Looks like it fits.
That looks about right. Which number did you use?
I just changed it to 0.6 versus 0.5. To...
Which 0.6 is 12/20, right?
Yeah.
So what that is that's a 10-tooth gear that uses a 12-tooth pitch diameter. Does that make sense?
I think so, yeah.
It's a weird kind of. Mr. Cross would be able to tell everybody a lot more about it. I don't actually know how that geometry works in terms of like how you develop that geometry, but it's a weird thing that gear manufacturers are able to do. And then we could benefit from it. Cool. So that looks good.
I have to work on some standoffs, another plate.
Yep. Well, you can probably use the same plate in your application here.
Yeah, so how did you do that? You just
You just straight up. No, you don't have to replicate. You just straight up copy. So click on your part.
Okay.
You might have to click on it over in the left pane. Maybe. Yeah, you can. There you go. Copy part 1 and then Control V or paste.
Ah.
And there you go. You've got 2 of them. What's cool about this is if you make any changes to the other one, they'll automatically happen to this plate as well. Because they're the same part. If you needed to make them unique parts, you do what I did previously, which was that transpose function, and you make it a copy. Use the configurable spacers. It'll be a little bit easier to use. Yeah. And you can use the nylon or the aluminum. It really doesn't matter.
I like aluminum.
Oh, they only have fixed length ones.
Yeah. Nylon, let's see. Where to put it?
It might be. Yeah, you can right click on it and isolate it, and then you can move it out of the way. There you go, or do that.
Oh, pretty.
Isolate is probably my most used like little kind of trick because it's so easy to lose parts in a giant assembly, or to not know what part you're looking at, or to not know like if it's interfering with anything. So right click and isolate is very, very helpful.
Now, I have to make 4 of those and keep making them? Like,
No, those should be the same part. So you could probably use a replicate command if you'd like, which is up at the top. It looks like a Lego, kind of, to the left. That's a pattern. That's replicate. There you go. So, and then you just click on that front face, or you can click on since you, yeah. Oh, do you see the blue box up in the top left? You're still in the instances to replicate page or selection. So delete part 1 out of there. You don't want to replicate your plate anymore.
oh, okay. Then I want to be here.
Exactly. There you go. I just built a bunch of spacers for you.
Although I didn't necessarily need them there. That was just for the motor, right?
Or you don't maybe need the ones on the outside.
Oh, yeah, I guess I could have just
You can bolt long bolts right through into the motor, and that could be how your gearbox is built.
okay. Yeah, save on plate space.
Save on plate space, save on bolts, save on spacers. And it makes your motor more easily able to be removed, right? Because now your bolt's on the outside of a set of plates and not on the inside. It's a little trick. A lot of teams do that. Sometimes it's more helpful in some places than others, but it's generally good practice.
Oh, we need another bearing. Let's see. The bearings, 6 bearings.
There you go.
Now, what come it doesn't turn the other gear? Can you make it actually do that? Like run a gear train?
You can. I'll show. In fact, if you'd like, I'll show you how to do that. Click the K button for a second.
The K button.
K. As in, like, literally the key on your keyboard. K.
Oh. That's not a button. That's a key.
Key, button, whatever. Okay, so K, all K does is hide the mate connectors. And if you click the J button, it does the same thing with mates. Okay?
Okay.
So now what I want you to do is click on, you should have a Revolute mate for your pinion gear. So right click on your gear and hit show mates. Is that for the gear? But you can just right click on the gear and hit show mates too if you want. Up a little bit, up, there it is.
I don't see it.
Oh, you were on it. There it is. So that's the Revolute. And then find the Revolute for the shaft. I think it's the shaft on the other one.
Yeah.
Whatever causes that shaft to rotate. There you go. So select those two mates, and you could just click it there, and then click the one right below it. Over on the left, back on the left. Yep. So click that one, and then the one below it.
This one.
Like select them right there. Yep.
Okay.
And then up at the top bar, where all like the mates and everything are, there's an image that looks like two gears that are meshing. So all the way to the right, further to the right. Further, keep going. Right there. Yep. So what this does is it takes your two Revolute mates and it makes a relationship between them based on the ratio. So there you go. You've got it. And now you have to tell it what the ratio is. So it's not a 1-to-1. It's and you could do math in here. So it should be a 10 divided by whatever.
It's a 62. Yeah.
Is it a 60? So then do 10 divided by 60. And then hit tab or enter. And now try it. It might be backwards. Yeah, I think it's backwards. So I think it's 60 divided by 10.
Okay. That's better.
That looks better. Are they going the right direction? Nope, they're going the wrong direction. So you have to click the reverse direction button. And now they flip direction. Now it should be an actual gear train mesh. Right? That looks about right.
Yeah, this one goes around many times, and the other one goes a little bit.
There you go. So for CAD practices and what we're doing, that's not always useful, and it is pretty like cumbersome on like the model, because sometimes just makes the model run more slowly. So there's many instances in which we don't model like gear rotations like that. But if you're making like a 4-bar system or some crazy linkage where you actually want to see it move correctly, you will model stuff like this. And I'll show you one more thing that you could do. If you right click on one of those Revolute mates, any one of them, it doesn't matter. Sorry, the one for the gear train that you just did. So like one of the first two.
Oh, okay.
Right click on that and do animate. See the animate button? You can hit play and it'll rotate 360 degrees, and it'll rotate both of them. And then it'll reciprocate and it'll go backwards. Yep. So that's a good way to show if you want to see how a mate moves or how like something reacts to another thing, you can display it here. But in CAD doesn't know that things are touching each other or interfacing with each other physically. You have to tell the program what the interfaces are, what the relationships are for movements, right? So this is a good example of that.
Yeah, that's super cool.
Yep. I'm gonna challenge you, Steve, to take off those other 2 spacers that you're not using.
Okay.
And then I might design or I might show everybody how to make a 2-stage drivetrain. Actually, Vihan, can you show us your progress up now? Oh, Steve, you won't even need to delete those spacers there. You just need to change your sketch that's defining that plate.
Okay.
And it should automatically update.
All right.
No.
You want to let somebody else present now? Hold on.
Yep.
I'll cry wolf in a minute here.
All right, Vihan, show us what you got.
And my computer is super laggy, so I haven't done too much stuff.
Okay, no worries.
So I ended up using an 18th tooth gear.
Okay.
Because the 12th tooth gear didn't have a hex. It was not a hex. It didn't have a hex.
Yep.
So I got this 18 tooth gear, and yeah, that's where I was trying to implement the Revolute mates.
Perfect.
Just one, with the bearings.
Perfect. Excellent. Good work.
Thank you.
And yeah, an 18 tooth should work. Make sure you change your layout sketch in your 2D part, right?
Yeah, I already changed that.
Okay, good. As long as you change that, you should be good. And this is the part of design where you can go back and forth. And like you can very easily put in different gears and put in different like center spacings and see what works with the gear train. And that's kind of the very iterative part of this like gear train design here. Especially in CAD, it's very easy to go back and forth and change things right now. Much more easily than it is later when you build the thing, right?
Yep.
Cool. Awesome. Good work. After you get your gearbox completed, you have a really good gearbox to set up so that it's not linear.
Meaning?
Meaning you see how you have your motor and then your first set of gears and the second set of gears are in line with those first ones?
Yeah.
I'm saying that you could put that second set
Oh,
anywhere around the circle. And so I'm going to use you later once you get yourself set up here as an example for that.
Okay.
Cool. All right. Isabella, would you like to share? Oh, you have a question too.
Yeah, I could. I know you said to fix my plate onto something. Would I do that in the sketch? I still,
Would you do that where?
like in the how would I fix my
Your assembly.
yeah.
You right click on any part and hit fix, but generally you'd want to do it to the plate.
Okay.
See the fix button? You're on the bearing right now. I would not suggest fixing a bearing because the bearing would rotate, right?
Right.
But I would fix a plate. There you go. Another option is you can fasten your plate to the origin. So if you undo that fix, if you do Control Z or whatever, isolate your plate. Right click, isolate. And start a fastened mate. And select the hole where the motor is. Either the top side or the bottom side, doesn't matter. And then click the origin, which I believe is to your right. Yeah, it's over there. That's the origin. But don't go that side. You're gonna have to move the mouse around until you're facing towards you. Like it's a little bit tricky. It's not super intuitive and it doesn't select very well. So just move your mouse around that whole thing until the mate is facing towards you.
Oh boy.
Remember, your view rotates around where your mouse is. So you want to put your mouse in places where you want to rotate around. Not over there, over top of the origin. I would say rotate down so that you're looking at the thing from the side a little bit more.
Yeah.
Also, if you get lost in space like that, double click the center mouse button. Try that.
Okay.
There you go. So now zoom into the origin again.
This
And
is
try-
the origin, right? I'm not crazy.
Yep, nope, that's right. Remember, it zooms to where your mouse is. Your mouse is not over by the origin right now, and that's why it's zooming away from it. There you go.
And then I just click on it.
No, it's got to be facing up towards you. Look at it from the side instead. You're looking at it from the front. Look at it from like the top of the bottom. Again, double click your center mouse button when you get lost. You got to do it
Yeah.
faster, I think.
Okay.
There you go. So look at it from the side. So as if you're looking at the cylinder from the, there you go. Now try zooming in and clicking on it.
It looks like it's facing forward when
Wait,
I'm looking at
you
it
don't
from the-
you don't need to zoom in so far. There you go. Now it's facing the right direction. Okay, now zoom out. There. So now your plate is actually attached. It's when you click the green checkbox there, it's going to be actually attached to the origin. And all the other parts go and fix themselves because the other mates need to be completed as well. Does that make sense?
Yeah.
And now try to click the plate and grab it and move it.
It's not moving.
Good, because it's fixed to the origin. The origin
Okay.
is the origin is kind of like the starting point, and it's the only point that doesn't move in space, in your model space. Okay.
Okay.
Everything else, if you don't tell it to be fixed anywhere, it can move anywhere and at any time.
Do I need my shaft on the motor to move so that my gears spin when everything's fixed, or?
Not really, but what's going on with your gear? Can you move your gear?
This one?
Yeah, what's going on with
think
that?
I think I accidentally mated it somehow.
Yeah, you're using a slider mate. And you've made it to the face of the shaft, not to like the round of the shaft.
Okay.
So did you just delete it for now?
Yes.
Yeah, that's cool. So do a revolute mate. But don't click on the face. Click on like the round of the gear.
Like
Like
here?
that. Yep, exactly. And then click on the bearing. On the round of the bearing. Yep. Now that's going to put your gear into the plate, but if you hit the arrow keys, See the little like the it looks like an arrow pointing up and to the right. Yep.
Yeah.
Like that. It flips the direction that the mate happens. So it's like it either puts the mate on top or the mate on the bottom. And now that's set up correctly. Now you have it in the right place. So you click
I
OK.
already had the bearing spinning on the plate though. Should I fasten it instead?
Again, for what we do, it's not super critical if you like fix the bearings or revolute the bearings. I generally fasten my bearings and revolute my shafts because that's kind of what I think about with how bearings and shafts work. Like the bearings you mount into something, even though the inside of the bearing rotates. That's just my take on it. Other people may disagree and they say, well, make the bearing rotate.
And what about for the motor?
What about the motor?
Oh, does that need to have a revolute on it at all?
Does the motor rotate relative to the plate?
Yeah.
Does it?
No, but like, does the shaft on the motor?
The shaft does, but the shaft of the motor is part of the motor part.
Okay.
So I would say no. Oh, you also did the same thing with your dad. Look at the space between the motor and the plate. Like, look at the top or the bottom. Yeah. Also, I'm going to give everybody a hint. The N key, click the N key right now, Isabella. N as in like Nancy. There
Like
you go.
normal.
Like normal. Yes. N will always take you normal, no matter where you rotate. So like rotate away again, like so that you're looking kind of at it from the front. There you go. Now click the N key. It will always face you to the closest normal position. All right.
Yeah.
And that's
Yeah.
super useful. Utilize that. So anyway, go back to looking at it from the side and click the N key. Now that gap there, that's not how motors are mounted, and that's going to get you in trouble because maybe you like think you had space there when you really don't, or maybe like there's something on the opposite end of your shaft that you're like, oh, I'm not running into that, but in real life you would be, right?
Yeah.
Because your motor would be fully against the plate. So I want you to try to find the mate where the motor is attached to. There's a few different ways you could do that. I would suggest right-clicking on the motor and hitting Show Mates, but that's just me. Show Mates. Oh, it's in there. Yep.
Oh, yeah.
There you go. And that's, I think, the one right there. So if you click on that, you double-click on it or edit it or select it on the left and right-click and edit. I want you to delete where it's attached to the brushless motor, to the Neo, and then reselect the correct edge.
Okay.
So you're going to have to rotate around till you see that. Or you can hide the plate. Remember, like your dad did, hide the plate on the left. Yep, over there. Yep, part 2, I think, is the plate. And there's an eyeball that will show up. Yep, you see the eyeball. There you go. Now select the correct edge of the motor.
This one?
I would zoom in a little bit just to make sure you're on the right one. That looks right to me. And now click OK. Green checkbox. And now unhide the plate. That looks good.
Okay. Should I
Beautiful.
I guess I should fix this one too since there's space.
I would probably, yeah, bring that further down, which I'm assuming you did an offset with that, right?
No. I think
I think you did an offset. Oh, you probably did. You made them center to center. So that's okay. You just need to put an offset in it. I'll show you how to put an offset.
Okay. Should I? Oh, here? Do I check it?
Yep. You click the checkbox, and that'll apply an offset, but everything's 0 right now. And I'll give you a hint. The Z-axis is the axis about the shaft, like that goes through the shaft. So what do you want to do? Yep.
I gotta bring it down from here to the motor plate.
Not all the way to the plate. Just like a portion of the way. So put in a number and see if it works. Like type in 0.25 or something. That looks like it's a little bit too far. We're going to try to use actual fractional values here. So I would try 0.25, but that looks pretty good. That's off of the motor.
Do I want it on the motor?
No,
Okay.
because that would have your gear rubbing against the fixed motor, right?
Right.
You want the gear to only be touching the shaft and the other gears. So I would do it at like 0.2 is fine, but I would do like 0.125, which is 1/8 of an inch. You can also type in 1/8 or 3/16 or 1/16. Like
It does math.
It does math for you. Yeah, try 1/6. Like if you're not good with fractions, you don't have to be. It'll do it for you. Let the program do the math for you.
Okay.
There you go. That looks good. Cool. Awesome.
I think I can keep building from here.
Sounds good. Sounds good. All right. So everybody keep working. I think we've gone through everybody, and I want to let everybody continue to work. So I might start a new little demo thing here. Maybe. Vihan, what's up?
So I'm having problems with my gears overlapping again.
Okay. Can you show your model?
Yep.
Okay. So how many teeth do you have on each of these gears?
So this one is a 48 tooth gear.
Okay.
This one is 18, and this one is 20, I believe.
Okay. Did you update your layout sketch to have a 48 and an 18 between them?
So 48,
That's good.
and then 40.
Yep.
What?
I said, yep. No, that looks good.
Yeah. And then this one's the 10 tooth.
Yep, but what's the one in the center? Is that? Yeah, that one.
18.
That's 18. They're all divided by 20. So let's do some math here. 18 plus 48, right?
Yep.
You said divided by 20 should give us a total distance from center to center of these gears. Can you click on the center ring of the furthest gear to the left?
Like this one?
Yeah, like that ring. Yep, exactly. And then click that same ring on the gear that it's supposed to be meshing to.
Here?
Yep.
Like this one?
Yep, like that. Yep, you got it. And in the bottom right, do you see down there? What number does that say?
1.5 inch.
1.5 inch. Okay. I think your center distance is supposed to be 1.65 inch.
Okay.
So I'm not sure exactly what's going on, but you definitely don't have the right center to center distance. I have a theory. Can you go back to your parts studio?
Yeah.
Parts. And can you click the checkbox?
Oh, yeah, it doesn't update it.
There you go. It doesn't update it until you finish the sketch, right? So now go
Yeah.
back to the assembly and boom, there you go. Look at that. Perfect gear mesh.
And do you think this would work? I was looking at it earlier.
So this is one of those weird gears that I was talking with Steve about, okay? So they use, what it is they have lesser number of teeth than what the pitch diameter is. It's
Okay.
confusing, okay? So I believe that is a 10 tooth, right?
Yeah.
In fact, click on that part. Click on that gear. Do you see in the left here? Open your side view up a little bit, like open that window so you can read what it's saying. So do you see how it says 10 tooth and then it says in parentheses 12 tooth center distance?
Yeah.
So what you need to do is in your layout sketch, you need to change it from 10 divided by 20 to 12 divided by 20, even though it's a 10 tooth gear.
Okay.
It's a little bit weird. They're very like specific gears, and it only works for the very small ones. So yeah, make that 12. Then if you click enter, click the checkbox, and go back. Now it should be meshing correctly, or should be the correct distance. And Vion, click the N key for me. I'm going to get everybody into the habit of using the N key. Wow, look at that. It's perfectly normal. So now if you zoom in, you can rotate the gears so that they're roughly in the place where they need to mesh. There you go. And that looks like about right.
Yep.
That they would actually mesh. Perfect.
So, yeah. I guess I'm done now.
So no, you're definitely not done. You need another plate.
Oh, yeah.
And also, I don't think your motor's mounted.
What?
Do you have any holes to mount your motor?
Oh, no.
So the holes for motor mounting, it's a 2-inch hole pattern. In other words, from the center of the gearbox, it's 1 inch to one hole in one direction, and then another inch in the opposite direction from the
Okay.
center of the motor. Okay.
So from like here, from the middle of there, 1 inch there.
You can go that direction, but I would suggest going the other direction.
Like that.
Yes. So
Okay.
it's 2 inches total distance between the holes.
Yep.
And through
Okay.
the center of the motor. So get that modeled in. You should be able to do that in the plate sketch.
Yeah. This here. Um.
I would try a line.
Oh, okay. A line?
Yep. You'll see why. Don't start it at the center. I mean, you can, but I'll show you a trick. So delete that for now. And draw a line out like in space somewhere, like way off the plate. Not even attached to anything. Okay. Now put a dimension on that line. Make sure it's not. Oh, nope. Do you see how that fixed it so that it was measuring perfectly horizontal?
Oh, yeah.
I want you to make this dimension so that it goes parallel with the line and it doesn't just go vertical. Okay. And that'll be important. It's not really important right here, but it will be important in other things you do. So I'm just going to show you and everybody else here. So just click the dimension, delete it, and then click dimension again. Point to point.
It's loading.
A little bit slow.
There you go.
And so before you click again with the dimension, just pull it out into space. So do you see how that's dimensioning horizontally? That's not really dimensioning the actual length of it. It's telling you just how far it is. Do you see how that dimension is dimensioning the actual length of the line, right?
Yeah.
Do you understand how they're different?
Yep.
Cool. So make that.
Click on the line itself. Do that sometimes.
Sorry?
Can't you just click on the line itself rather than the points?
You can, yeah. That's a valid way to do it. Now, Vihan, that's going to be a 2-inch line, not 1 inch.
Yeah. Okay.
No, you don't need to make another dimension. Just edit that one. Yeah, double click
Yeah, I
that.
was turning it off.
Yep. And then I want you to click the line. Yep. And then click the center point of the circle that you're trying to go to. And we're going to use a new
midpoint.
Yes, exactly. You see where I'm going. It's over to the right. That's coincident.
Oh,
Midpoint's way over to the right. There you go. Now make that line vertical if you want, or however you want to make that line, but I would make it vertical. And also make that line construction geometry.
Yep.
because we're not actually using that line to do anything. We're just telling it where holes need to be.
I'm gonna. Yeah.
Cool. All right. Good work.
Okay, sorry.
You can use the Q key too, remember.
Yeah.
Q is the shortcut for construction geometry. Remember those shortcuts, they're important.
And then
All right.
I'd use the circle.
And then you can make circles. Yep. Just to let you know,
How
that's
big are
one
the
way. That's one way to make holes. There's also an actual hole feature that will help you make holes of the right size. Do you want to try to use that feature?
Sure, I guess.
Okay, cool. Delete all of your circles then.
All of them?
Yes, but keep the other
Um,
points and lines that you're using to reference it. Oh, sorry, not the circles for the bearings, but just like the bolt circles. Yep, those.
Are these. So
Yes. So delete all 5 of them.
these two.
Yep. I commend you for doing this with a laggy computer. I know how difficult that is.
It's a really old computer.
Mm-hmm.
Okay.
All right. So
So-
did you get the one on the top left too?
Yeah.
All right, cool. So I want you to click the green checkbox. And so you no longer have those holes in the corner of your part anymore, but that's okay. I want you to turn visibility on for that sketch that you were just working on. So do you see how it's kind of like dark there? Yeah, click the little eyeball. You got it. And now you can see where the holes need to go, right?
Yep.
So there's a feature. Do you know where the extrude button was? Do you remember where the extrude button was? To the right of extrude, there's one that looks like a hole in a part. That's called hole. Nope, way further over. Way over. Keep going, keep going, keep going. Right. Oh, too far. Way beyond.
Okay.
Back. There it is. Yeah, yeah, yeah. So this is the hole feature. The hole feature is really, really great for generating the right size holes for you automatically.
Yep.
And you not needing to remember like what diameter for what size bolt, and whether you need a tap size hole or whether you need a clearance size hole or anything like that. So you're going to do through holes, and your standard. Do you see where it says standard there? Click that drop down.
Standard.
You see where it says custom?
No.
It says standard, and
Oh,
then it says custom. Yeah.
Yeah.
So click that and do ANSI, which is like the American Society of, or the American National System Standards Institute. I think that's what it stands for. It's a way for us to use common bolts and common things. Like this is why like you can take an outlet at school and use the same outlet at work, or the same plug at work or at home. Because if we didn't have standards, we'd have a million different types of these outlets.
Yep.
So we have standard size bolts. So the bolts that are used for these types of motors are number 10 bolts. So do you see the size thing there?
Yeah.
There's the size. Yeah, click the drop down on size and go to number 10. There you go. And a free fit is fine, but if you click on the free button there, this is how big the hole is relative to the bolt. You could have be a really close fit, which means that it'll be just barely bigger than the bolt, or you could have a normal fit, or you could have a loose fit where it's significantly larger than the bolt. So for our applications, free fit is totally fine. And now you can select the positions of the holes. So that blue box that you're in right now is the sketch points to create your holes. So all you need to do is select the points where you want your holes.
So here.
Yep. And you'll see it'll automatically make the holes for you as you click, each time you click.
Yep. You see that?
And don't forget the motor ones too.
Yep. Here. Here. Now, how do we like make them separately? Like for example, the motor holes one, they're either I think they're smaller than the outside ones, right? Or are they the same size?
So, for our purposes, we'll make them the same size, but that's a really, really good point. If you wanted to make these two different sized holes, you would only use the hole feature on the holes of one size, and then do a second hole feature for the other ones that are a different size. Okay?
Yep.
That's a fantastic, fantastic question. So you're going to need a hole feature for each different sized hole. And what you could do is you could name your hole feature. So do you see where it says hole 1 there? Right next to the green checkbox, you'll see a little, yep, there you go. And you can call this number 10 clearance. Well, no, like a hashtag, like a ampersand.
Oh, yeah.
Or not ampersand, like a, what is that thing called?
A hashtag?
It's not, it has a name previously before hashtag, a dial tone, I think is what it's called. No, that sign means number, by the way.
Oh,
Just
yeah,
so you know,
sorry.
that sign means number. So when I say number 10, you say that sign and then 10.
Yeah.
And then type clearance just to tell whoever is using this model that's a clearance hole.
Yep.
Yes, Onshape does have spell checker. It's okay, I'm a bad speller too. So then you can click the green checkbox. And now you have a hole feature.
Yep.
Oh, it didn't like the number sign, I guess.
No.
Whatever, not a big deal. Cool. So now if you go back to your assembly, some things might have broken because we changed how the holes were defined. So when old faces go out of existence and new faces come into existence, they're kind of like, oh, where'd my old faces go? Where'd my old reference geometry go? But fortunately for you, you haven't mated the standoffs yet. So you had no broken mates.
Cool.
All right, awesome. Good work. Does anybody else have any questions at the moment or would like to share their progress?
How do we animate the gears moving?
Isabella, can you share your screen?
Sure.
I will reiterate, animating the gears moving is cool and it looks good, but it's generally not, like, it's not really necessary in a lot of the design that we do. I'll put it that way.
Yeah.
But I'll show you how to do it because it is a cool thing to do and it's a cool thing to show other people as well. So click get normal. I always like looking normal to things. Yeah, look at how much better that looks. All right, so you need to select two mates that are revolutes. And you need to know the number of teeth in your gears as well.
Right.
Right.
Like I get that and I know. I was just wondering because I know this one isn't revoluted yet. And
Well, then you're going to need that to be revoluted. You can only do a gear relationship between two revolute mates.
Okay.
Actually, I don't think that's true. I think you could do it with other ones, but it needs to be a mate that allows it to rotate. I'll put it that way. So good. You just edited the mate for now. That gear should rotate. So you should be able to select that gear and rotate it. Right. Beautiful.
Okay. So then.
So now, yep, you select the gear function and then select not the part, but the mate. Yep. The two different revolutes.
I labeled these.
Very good on the labeling. And then you need to put in the gear ratio between the two, which is
1:1.
it's not a 1-to-1.
Oh.
That is not a 1-to-1 gear ratio.
It's not. It's 60-12. So I'll just put 5-to-1.
Or you could type in 60 divided by 12 if you don't know what the division is for that. Because this program does math for us. And then click and try to click on the gears and see if you can drag them and rotate them. Are they going the right direction or no? Doesn't look like it to me.
What do you mean by right direction?
Are they going like this? Or are they going like this?
Oh yeah, they're doing the latter, not the former.
So then you want to do reverse direction. Do you see the button on the left that says, yeah. So now try to grab and move them. Actually, they were going the right direction, but you have the ratio backwards. So instead of 60 divided by 12, do 12 divided by 60.
Okay. That makes more sense.
Now click and drag. There we go.
Thank you.
That's a meshing gear. So now you can click OK. Yep, there you go. Good work.
Thanks.
Anybody else have questions? All right. I'm trying to think of what I can go into next. I might make a gearbox with a pulley and one with a sprocket. Because those are two very useful things. Gears, I think, are the most useful things to design, but sprockets and pulleys are also important, and they have different use cases and different benefits and drawbacks, each of them. So let's draw one with a belt. And I'll show you guys something called a feature script with that. So a feature script, wrong window. Let's do the right one this time. Feature script is a program, just like all these other features here. It's written using a program and a programming language. And it basically does custom things. It makes custom, it's a custom feature. It does something unique that has been programmed by somebody individual. So the cool thing about being an FRC is there's like tens of thousands of people that are involved in it that are all trying to do something similar. So they're able to build like really cool custom features that are useful to the rest of the community. And as you can see, I have a bunch of these here, and I can show you how to add these at a later time. I have probably too many, but I'm going to use this one called the Frc Belt Calculator. And what I mean by belts is Htd belts. You've probably seen them before. They look something along the lines of this. You see them commonly in cars all over the place. They're really useful because they're lightweight. They can be variable distance from each other. You can get belts in a lot of different sizes and lengths. They're easy to replace when like a belt breaks, generally speaking. And I mean that's the most of the benefits to them, but it's just a good idea to know how to design for them. What's up? Somebody unmute.
Yeah, when's a belt better than a chain?
A belt is better than a chain in terms of weight. A belt is almost always much lighter than a chain. because for a chain you need a sprocket and the chain itself, which is almost always steel and it's significantly heavier. A belt can also have a smaller minimum size sprocket, so it can take up less space and have a larger reduction in a smaller gap. It's like a sprocket, you can only really get like a 4-tooth sprocket. It's, I think, the minimum that you can get. And a 4-tooth sprocket is the same outside diameter as like a 10-tooth pulley, or 10-tooth, 10-tooth belt pulley. Does that help answer your question?
Yeah, I think so.
Perfect.
The chains allow you to do more power distribution now? Or?
Yes,
Oh,
chain has a lot more capacity for torque transfer, for actually transferring torque. Belts will skip if too much torque is applied to them. Where chains, if they're properly tensioned, you'll never ever see a chain skip over a tooth because they're so large. But they're used generally in very, very similar applications. Chains also have a thinner profile, like the width of a belt is usually wider than what a chain is wide. So there's another kind of pros and cons. But generally speaking, belts are used commonly in like the very first reduction from a motor to something in a gearbox to have a really, really high reduction in a small space while also saving weight. Belts generally don't have backlash like a gear train does. If you properly tension a belt system, it will have nearly zero backlash. And by backlash, I mean, we talked about this before, but when they have a little bit of gap in between them, they can do this in between the gears. And that's called backlash. And if you have too much backlash, you can actually shear teeth off because you move one of the gears and it very, very strongly impacts the next gear tooth. And it can totally shear the gear off if you have too much power. So belts are good, and when you design belts properly, they can be very light, very efficient, and very effective at creating large reductions in a very, very small space. So we're going to try to do a belt reduction. And what I'm going to do is I'm going to use I'll show you a Neo 550 motor, which is a different kind of motor. And for those of you on 272, you've seen us use these motors. This was the motor that was used for the turret this past year. It's basically, it's a 550 style motor, but it's a brushless version of them. So here's the Neo that we were using earlier for our little drivetrain gearbox. Here is the Neo 550. And we're going to use that motor in our gear train here. So I'm going to go to the motor data sheet and then also the drawing. So the data sheet has all kinds of stuff about the RPM and the current, and it also has that motor curve that we had talked about previously. So as you could see in this motor, the peak efficiency is right around 10,000 RPM, but the peak power output is right around 5,000 RPM or close to 6,000 RPM. So it depends if you want efficiency or if you want power output. Generally in FRC, we're less worried about efficiency. We don't care how much power the thing uses. We want it to be as quick as possible, which means more power. So when we're designing using this motor, we're going to try to shoot for like this speed range. And what that does also is allows us to go faster if we need to go faster, but also go slower if we need to go slower. So let's say, I don't know, let's see how much of a reduction I can make in this pulley on in a single reduction. So how to design for pulleys is very similar to how you design for a gearbox with gears, except you don't necessarily need to have, you don't have the circles tangent to each other. So you have one circle like this and you have one circle like this, and they're not tangent to each other. And you can, if you want, draw the lines like this and make those tangent. So, and that'll just show you. It's not really useful in terms of like designing it, but it is useful in terms of showing you where the belt is going to run. And the idea of pitch diameter with belts is exactly the same, except the belt pulley pitch diameter calculations are just a little bit different. And what I usually do to do this is I go to a belt calculator. There's all kinds of them online. And the most common one that I usually use is this West Coast Products one. This is a company that makes parts for First. But there's also this guy here that is Recalc, which is, this is a calculator that's used specifically for FRC. And it's got all kinds of stuff. And it also shows you part numbers and places where you can get these belts. And you can click on this, and this will bring you to the vendor's website with that specific belt or pulley. So Recalc is freaking sweet and powerful. So I'm going to use this for example. The common belt type used in FRC are either 3mm pitch GT2 belts or a 5mm pitch HTD belts. And the letters, all that means a different profile. So like the HTD belts have a more rounded side, and the GT, what type of GT2 belts, they have a more like trapezoidal shape if you look at their shape. These ones are rounded. Maybe I'm thinking of something else. I think GT. Yeah, I guess GT2 and HTD are the same. There's another one. Maybe it's GT3. I don't know. I don't know exactly the different terminologies, but oh, here's a GT3. It's got a little bit different of a profile rather than just being a straight up round. And so you need to use the right pulleys with the right belts. But just as a demonstration here, we're going to be using HTD belts, and we're going to be using a 5mm HTD belt. Let's say our target center distance is, I don't know, 3 inches. We don't want any extra center, and we don't want to use a specific belt teeth. And let's see what's the smallest pulley that we can find. HTD. Well, maybe they don't sell HTD belts. So I'm going on the Rev website to go and find some belts and see what kind of belts they offer. So they have 3mm pitch GT2. So we'll go with that actually. Instead of the 5mm HTD. So 3mm. And let's see what the smallest pulley is that we can find. GT2 3mm pitch pulleys. The smallest one is a 12 tooth, but they also have pinion gears, which are pinions that are attached to the 550 motor, like that. So we're going to look at that one, and they've got a 12 tooth 3mm GT2 pinion. So that's what we're going to plug into here, 12 teeth. And then we're going to go back on the Rev website and see what other GT2 pulleys they have. It looks like they have a 36, 48, and a 60. Let's do the 60 just because. So we're going to do a 12 to a 60 tooth. And it looks like the minimum belt length that we can use is an 85 tooth belt length, and that is going to be 2.7454 inches in distance, center to center. So what this is telling us is the center to center distance, whereas before when we were calculating like this pitch diameter and this pitch diameter, and we were calculating what that center distance was, with belts, it's usually more useful to go into a calculator and calculate them. So if I use that 2.7454, so dimension, I'm going to dimension not the circle, but from the center to the center of the other. I missed that center point. This is the important dimension that we're measuring. And that was 2.7454. 2.7454. All right, so that's the center distance. And we're going from a 12 tooth to a 60 tooth. And it tells you right here the, maybe it does. Here we go. It tells you the pitch diameter. So the pitch diameter of a 12 tooth GT2 is 0.451. So I'm going to do dimension here, 0.451. And the pitch diameter of a 60 tooth pulley is 2.256. So this one's going to be 2.256. And I wonder if I could use a smaller belt. What if we used a smaller belt? What if we went to 2 inches? We went to 2 inches, our center becomes 1.7791. So I'm going to try that. 1.7791. And the reason why I'm trying to go smaller is because maybe I'm trying to minimize the overall size of my gearbox. And that seems like a reasonable way to go. So this calculator, it automatically changes the number of teeth in the belt you could find. And it automatically gives you the pitch diameter and links to places where you can buy these sprockets, or these pulleys, I mean. Super, super useful. In fact, I'm going to copy this and post it in the chat for everybody. Recalc. There's also this belt calculator from West Coast Products, which I have used a bunch of times. And there's other ones that exist out there. There's one built into Onshape that I can go through later, but I just wanted to show you how to do this if you didn't have the one built into Onshape. Cool. So that's our first belt reduction. And let's say maybe we want to do a gear reduction after that. Let's do the layout for the gear reduction. So I probably want a small gear. And I think Vihan figured out that the smallest gear in 20 DP that you could get in a 1/2 inch hex shaft is an 18 tooth. So I'm going to do 18 divided by 20. And then I'm going to have another circle that is tangent to that one because I'm making gears now. So in this gear train, I'll reiterate, I have a pulley reduction first, and then I'm going to have a gear reduction afterwards. And I'm using the gear reduction because I have more torque now. I'm afraid that if I did another pulley reduction, that I would slip with my belt. So instead, I'm going to try a gear reduction. And maybe we want to go from an 18 tooth gear to a, I don't know, 48 tooth gear divided by 20. All right. And notice how I didn't constrain like the position of these at all, except for where the motor's mounted. And that's so that we can kind of do this and see what best works for our application. If we want to make this as tight and close as possible, we can maybe do something like this and have the hole for the shaft be very, very close to where the motor is. So, and then I'm just going to draw one more circle, and that's going to be the outside diameter of the motor. And if I come to this, this is all the documentation for the motor. The outside diameter is 35 millimeters. Do remember that in Onshape, you can type in whatever unit you want, and it'll automatically do the math for you. Convert it to whatever unit you're currently using. So that's where the outside of the motor is, and maybe here I'll do the whole pattern for the motor as well. So Vihan, remember I made a line out in space, kind of, click the center of the motor, click the midpoint, and then how far are the holes in these motors apart? They are 25 millimeters apart. I'm just going to do 25 millimeters. And I'm going to make this line perpendicular to this line so that my holes are never in the way of where the pulley is. I'm going to make all of these construction geometry because I'm not trying to extrude any of this. Let's make the pulley reduction be completely vertical, and then we're going to see how far we can get this gear reduction to go to this motor to try to minimize the overall size of this gearbox. Okay. So I'll let this float for now, or maybe I'll put like an angle on it. Vihan, what's up?
So I need to change the length of my spaces. How would I do that without like deleting it and restarting?
Let me stop sharing and I'll show you. So if you could present.
Yep.
All right, so click on one of the spacers. Now, do you see how the part over in the left over there has a little blue box next to it, right?
Yep.
That means that it's a configurable part and you can change the dimensions or something about that part. All right?
Mhm.
So what I want you to do is right-click on that part. And the first thing that you're going to do is select instances with the same configuration, which is a button right there. There you go. So click that. Now that selects all the parts so that you can edit them all at once. Okay.
Yep.
And now right-click the part one more time. Over there, that's fine. And then do change configuration.
Okay.
Up. It's a little bit further up.
Yep.
There you go. Change configuration. So this is where you can adjust the configuration of parts that are configurable.
Yep. All right.
So right now you currently have an ID, an OD, and a length of those numbers, but you can now change them to whatever the heck you want.
Cool. Thank you.
Yep. All right, I'm going to share again. I might not be able to finish this gearbox, but hopefully we'll be able to see where I'm going with it. So for now, I just put a dimension of here on a 45. And that's just so that I have a fully constrained gearbox. Later, I'll probably want to do something a little bit more, like smart is probably the word that I would say, like something that actually makes sense instead of just doing a degree. But for now, this will do perfectly fine. So I'm just going to call this belt and gear train layout. I'm going to finish that sketch for now. And then I'm going to make a sketch for now the bearings and the holes for the motor. Oops, I forgot to make this construction geometry too. There we go. So I want to put a hole everywhere where there's going to be any kind of a shaft, like where the motor is and where this shaft is and where this shaft is. Okay. And that's just good practice because that's generally where we're going to have bearings. And on these two, I'm going to assume that we're using the same sized bearings. So I'm going to click the equals button. And the common bearings that we use are 1 inch and 1/8. And these are numbers that I just know off my head because I've designed so many of these gearboxes. But I would suggest if you don't know this, finding the bearing that you're considering using, take measurements off of it, and then plug those numbers into here. And then I don't know the size of the hub on the motor. So fortunately, I left this data sheet up from the motor. And it looks like that hub in the center is 13 inches in diameter, or 13 millimeters, sorry, in diameter. So that means I can go right back into my CAD, type in 13 millimeters, and it'll do the conversion to inches for me automatically. And I already have the points for the bolts, if that's where I want to mount my motor. And now I just need to make a plate around this. But there's one more thing that I need to consider for the plate, and that's how I'm going to hold the plate together. This hole where it currently is will need to go through a gear, which isn't ideal. And this hole's maybe okay, but I don't have any other places over here where I have holes. So what I'm going to do is I'm going to draw this circle over here with construction geometry, and I'm going to make a tangent to both of these circles. And I'll show you why I'm doing that in a second. I'm just going to make it, I don't know, 0.5. We may have to change this later. Maybe I want to make it bigger than that, 0.75. We may have to change that later, but for now, that's what we're going to do. And then I think I probably want 3 places to mount this thing. It's usually a good idea to have like 3 bolts in different places. So I'm thinking that I'll want one here-ish as well. And maybe one like, I don't know, here. And you'll see what I mean, maybe. You'll see what I mean later about these. So I'm going to make these all, for the time being, equal to each other. I'm going to make this tangent to this. What these kind of dummy circles that I'm making are going to be is they're going to be where standoffs are. They're going to be the center point of future standoffs. For this, I'll make a tangent to the motor, and I'll also make a tangent to this pulley position. All right, so they're not actually real things. They're just little kind of helpers to help us put a standoff in roughly the right place. And for now, I'm just going to draw a big box around all of this, but we're going to make a more complicated plate later. So this is going to be the actual position of the plate, and I'm going to make it 1/4 of an inch from that, same distance from this, same distance from this, and same distance from this. Again, I suggest that you make these not individual dimensions and that you like draw a line so that you can change them all at the same time. You draw like a line from here to there, and a line from here to there, and a line from here to there, and you make them all equal. That's a better way to do what I'm trying to show you right now. I'm just trying to get through this quick because I have 5 minutes left. So, okay, this is going to be called my plate layout. And I'm going to click extrude on that. And I'm only going to make it 1/4 of an inch spot thick for now. I'm going to go copy the bearings that I used over here because I already have them. And I could search for them in MKCAD, but I'm not going to bother right now. So Control C, Control V. Oh, I need to make an assembly with this part first. So this is a part studio. This isn't an assembly, so I need to make an assembly that has this. Control V, that brings in my bearing. I'm going to insert that, where is it? Here. This plate. And the first thing that I'm going to do is fix it so that it can't go anywhere. I'm going to make my bearing to the plate. Flip it because it was backwards. And then I'm going to copy that same bearing and do another mate to the other hole. I'm going to insert a Neo 550 motor. So I'm going to go scroll down to motors and find the Neo 550. Oh, and look at that. This has a built-in pinion addition. So I don't even need to search for that 12-2 3mm GT2 pulley. It already has it built into this model for me. It's kind of like cheating. I feel like it's cheating because I used to have to design this stuff all on my own without any help from these things. So anyway, I'm going to take the motor and mount it underneath here like so. I can do it that way, or I could do it, oops, flipped. So now I've got the motor here with the pinion. Oh, there's a little bit of a problem, and that's that I'll do a little cross section here. You can see what I'm showing. Do you see how the flange of the GT2 pulley runs into the plate? That's a bit of a problem. So I have a solution to that, and that's I'm going to make another notch in this plate that will allow the pulley to still rotate right there. And so I'm going to go back to the part. I'm going to do a new sketch, normal, another circle that's bigger. Make it, I don't know, 0.75. And then extrude, remove, not through though, maybe only like 1/8 of an inch. So it's only cut in like halfway through. I think that's right. There we go. You see that? Now I made that little relief. And now if I come back to my assembly, I've got that relief cut into the part. So it no longer will rub this pulley on there. It's a fun little trick. All right. With 1 minute left, I'm going to insert a pulley. These are going to be the GT 3mm pulleys, and I think I did a 60 tooth, which is right there. And I just mate that with a revolute to the edge and then to the outside edge of the bearing. And it's upside down, so I flip it. And so that's where the pulley will go. It looks like this guy has to come up a little bit, and that's okay. And then on the top of this, we said that there was an 18-inch. So that there's an 18-tooth pulley, right? 18-tooth. Do aluminum, insert. So this guy, we're going to mate it to the other pulley. We're going to fasten them together because the pulley and the gear rotate together. So I'm going to go like that, flip it, and I need to make a little bit of an offset. Actually, that looks pretty good. And then what did I say the other gear was? I forget. So I'm going to go back to the sketch, go back to my layout, and because I did the math, I can just read off the value that I calculated, which is here. And it's 48. So I'm using a 48-tooth gear. So I can come over here in 2 gears. Actually, I'm just going to copy this spur gear because it's a configurable gear. Oops. Control C. Oops. Missing my Control C. Control C. Control. And then I can change the configuration just of this gear, change configuration, to instead of the 18 tooth, but the 48 tooth aluminum gear. Right? So now we have the 48 tooth, and now I'm going to do that a revolute about the bearing and about the gear. And I'm going to set that. This is where I would use an offset to get these gears to line up. So I would make that offset like 2. It's probably too far, and I'm going the wrong direction. So -1, -0.5, -0.625. That looks right. There we go. And so now I've just, you could see now if I put shafts in here, and if I put a plate on the opposite side, and if we put some standoffs in here, we have a really, really, really compact design for a 2-stage reduction gearbox. And it's pretty light too, because in our first reduction, we have a pulley instead of gears. And it looks like I could even bring this gear closer to the motor if I wanted to, because the bearing doesn't run into this pulley. So I'm going to do just that. If I go to my belt and gear train layout, I'm going to make this 45. I'm going to make it 30. We'll see if that's too close. I think it's going to be too close. Yeah, that's a little bit too close. So let's try 35. You can see this is where the iterative part of design comes into play. Let me bring this back upright. You can go back and forth with these gearboxes and change a little bit of them back and forth until it works. And that right there is crazy, crazy compact. And that's a, let's figure out what the total reduction is on that. We've got 60 divided by 12, which is already, that's a 5-to-1 reduction already. And then we've got an 18 divided by 48. Oops, 48. Sorry, 48 divided by 18. And that's a 2.66 reduction. So the total reduction is those two numbers multiplied. So 2.66 times 5. And it's a 13-to-1 reduction. So for every 13 revolutions of this motor, this output shaft will only rotate once. And that's a pretty significant reduction in a very, very, very tight space. That is useful for things like when you need to lift heavy weights for your game, or when you need to like rotate an arm that needs a lot of torque. This could be a good application for that. Or maybe when you need to lift the robot up off the ground, right? When you're trying to lift all 120 pounds of your robot, this could be a really good gearbox at the start of a really good gearbox for some kind of a winch. And it's 9:05. We've gone a little bit over, but hopefully this was useful, and continue to work on your own designs. Mess with pulleys a little bit if you're interested in them, and use those belt calculators. And let me know if you have any questions.
All right, bye. Thank you.
See ya. Have a good night.
Thank you, Phil.
Yep. Thank you.
Thank you.
Yep. Bye.